Start recording. Okay, so today's not lecture, today's assignment video, we going through matrix and apply the dry method. Okay, so we're going to do two things today. First of all, um, we're gonna implement matrix in C++. Second of all, we're going to implement the function using the dry method, which stands for don't repeat yourself. So what this principle means is that uh, throughout the whole source code, right? If you already written a function for it, right? Do not do not write the function again. Instead, just use the code. It's something like code reuse, which we're quite familiar with. So first of all, let's look at how to make a matrix in C++. Oops. So for matrix in C++, right? What for a matrix, the matrix is you can imagine it as a grid. So as if you're familiar with grids, you have a row and a column, which means you need to have some sort of 2D array, right? But for this case, since we're using C++, let's try using a 2D vector, right? 2D vectors. So today we're going to learn new thing for a 2D vector. So how does a 2D vector work? Okay. So how does a 2D vector work? Uh, so what's happening, right, is that when you have rows, a row is a vector, right? And here, a very good use of space. Let's draw another one. Alright, so you have a row of vector here. Row of, oops, row of vector. Then you also have a row of column. So this is our column. It's like you can try to imagine how to implement it. I'll just tell you the answer. Like how we normally implement a one-dimensional vector, 1D vector. We'll just have a std vector. Then we have the type, and then we have the whatever values we can construct inside. So what we can understand is that this vector contains elements of int. Right? So I think that gives you a clue on how to create a 2D vector. For a 2D vector, we'll want a vector. We want a top vector, right? The top layer to have elements of vector. Does that make sense? And within this vector, within this vector inside, is where we store all our values, like 0, 1, 2, 3. Right? So the vector, this vector will store this vector inside. And then we'll have a matrix. Cool, right? So let's look through the code. Let's see if there's any challenges that we might face with your understanding. Okay, so this is our class matrix. Implements a 2D matrix. Let's see. Let's close out this first. Where's our file? solution. Okay, that's right here. Okay, for private, right? We have just have three different data. Three different member. So we have the 2D matrix, which implement like so. A vector within a vector of type T. So T could be int, char, string, whatever. So if you have a string, it's like a multi-dimensional container. Then you have the matrix row size, which is the top matrix, the top vector, sorry. And then you have column, which is the inner vector. Right? And then the functions that we have to implement in order to use a driver file, compare operators, means plus, minus, times. Then the attribute assignment operator is equals, plus equals, minus equals, star equals, and output string operator. And then we have accessors for the rows, column, data. Alright. So all this, if we manage to implement all this, we'll be able to run this code. So when it comes to testing by yourself, try to run one by one. Right, comment out everything else first, except for this. Change this to 1, comment out this 2, and then comment out the definition. But I won't do it. This is going to be a fast one since we went through all this before. So you can use all this. This is actually not used much. You can skip this part if you prefer. And then we have our constructors. So in this case, right, we do not want to create an empty matrix, because an empty matrix serves no purpose at all. So the empty matrix will be when we create a matrix like M1, and we didn't give it any values, and then there will a default construction. The compiler will use the default constructor to initialize a class matrix with all 0 values inside the vector, which is quite useless. So we don't want it, right? The way you remove default constructor is to equals meaning, right? And then now for our normal constructor, construct the HLP2 matrix object being the size of row and column. So for this one, what's happening here is that let me just visualize it using the whiteboard. So what's happening here, right? When you create a 1D vector in the past, oops, there's no space there as well. 1D vector. Let's say let's not do this. Let's say back, right? Then I create this back. So this is the name that you give it. This is a variable name, and then you will give it this will be the number of elements inside. So number of elements. And then you will have I think you have whatever's inside. Right. You have all the data inside. The number of elements and then data. So if we're making a 2D array, right, what we're doing here is that we're making this into another vector. You don't need to give it a name. But this will be the number of elements. And then the data. Whatever the data might be. Right? It shouldn't have this inside. So this is what's happening here. For this one, you will have R, which is the amount, which is the row size, and you have vector inside. Then within this vector, right, we have another bracket inside. Like just imagine it like that. Right, this bracket belongs to this inner vector. This inner vector will have the amount. It will have C amount of rows. Okay. Yeah, columns. Sorry. So these are the columns. These are the amount of elements inside this vector, and they will all be initialized to 0. Okay. So this is how you create a vector with rows and columns. Instead of this, you're just creating an empty vector with empty rows and empty columns. So there's no rows, there's no columns. There's one row. Yeah, this just doesn't make sense. So this doesn't make sense. But with this, right, you're creating a matrix with that initialized to a value of 0. And then let's say if you want to copy copy constructor, it's just like so. Just copy the data, copy the row and column, and then for each row and column you just store. This is overloading again. I already done overload, so that's why I can use it like so. What's happening here is just RC equals to RC. Basically the row and column of this data equals to the row and column of whatever you copied. I think I don't have to go through that. Yeah. Yeah. Okay, this one is just the same. So what I want to book. So now I already went through how to create a vector matrix. There's one function about vector matrix that is very interesting. Is that this double double bracket. Right. Just imagine how you're supposed to get the value within the vector, right? I look at you. How are we supposed to get this? I mean, like if we use the operator overload, right? We will overload operator bracket. This is how we can get our original. This is how we used to get our original like array or vector. If we want to access the element inside, we use this operator. But there's no such operator as double bracket, right? This does not exist. You only have this operator bracket. So we just analyze how a 2D vector is created. The way it's created is that it has amount of elements of vectors, right? This is a vector. This is std vector. And then the vector contains this. Right? So let's just try this. Okay? What if we, instead of returning elements inside, we return the vector inside? So we just return vector. And then we will accept a matrix reference something. RHS. Right. So we will reference. So this is our operator overload. And then inside this, we will just return matrix. This. Right. So this will return. Oh, it shouldn't be RHS. Should be size t index. Right. So we'll just return whatever's in the index. So when you return the index, right, what happens to the double bracket, right? Just double bracket data R C. So what's happening here, right, is that first you run the code compiler series, a matrix class with an operator overload of R. So you'll run you will run this one first. And then this will become a vector, right? Then this will become, so we don't have to implement because this is already in a standard library. And then this will be where we get our data from. This will be the value. So you see, if we create a matrix using vectors or array or just any standard library containers, right? Most of the work is already done. You don't have to create another object that returns this. You can just use whatever's in the standard library. And it is all done by itself. Well, all we need to do is just implement this. And then by magic, by compiler magic, we're able to do this. So let's observe it over here. Do I have it? Right, yeah. So all I have is one single line. And I just return data. It's pretty neat. You don't have to do much. Right. So this is one implementation of try, where you just use what you have done before. Now, same thing here. Even though they both look the same, right? They cannot be like if you want to implement for dry, right? I remember dry you're supposed to say don't repeat yourself. But this one they're basically the same. But for for loops, right, you're not able to implement the principle because you don't the DIY dry principle works off on code reuse. But in this case you can't really reuse for loop because for loops are their own function. And then yeah, then for this you can't really use this as well. Because this is a copy constructor. This is a copy assignment. So yeah, this is not a constructor, you just yeah. And then let's go through okay, all these are hidden. Oops, spoilers. Alright. Oh, this is so spoiling. So we have all these small overloads inside. These are all the how you say art it's your maths assignment, not math assignment, but this basically where you just only have let's say this is the one where you just if you were trying to do addition, x equals to 10 x equals to so let's say x equals to 10, right? And we want it to and y equals to 20. So we want to find the sum of x and y. So we put x, or you want to increase x by y. We can do x equals to x plus y, or we can do x plus equals to y. It's the same thing, right? So this is what's happening here as well. So that's why you only need one, and at the right hand side, you only need one. But I guess from here you can really tell how we can apply our dry principle. So let's if we go through the minus, there's nothing much to say. All these minus plus operators, what we've done all along. Just need to look through the loop. Just add an array of and you just need to access the data inside that attempt, right? This plus equals is using the standard library because when you do all this, you get in at the end. I mean, you get the not in. When you do this, you get the position, the L value, and you just but this is the in, the address of the in. You just plus them together, and then the C++ compiler will handle it for you. But this is not overloading. This is not this. This is the standard library doing this. Okay. Same thing with minus. Just same thing with plus, minus, all this. You just look through everything, right? Star, you do the same thing. This is matrix multiplication. Oh, yeah, matrix multiplication is it's complicated one. That's why you need a third for loop. You want to look that up? You do that. I'm not going to explain matrix multiplication. This is scaling, so it's just one thing, and then yeah. So okay, this one we can explain how it works. So let's say we want to scale a matrix, or let's not scale a matrix. Just in general, if we want to multiply stuff, will you guys agree that x times 10 equals to 10 times x. They're the exact same thing, right? So what if the compiler calls, like, say, oh, I want y, I want z be equals to x times 10. Then you do this, right? You overload for this. But let's say we also want to do x, maybe another, for the w equals to 5 times 10. But 5 times 10 is the same as 5 times 10. 5 times 5 times x is the same as x times 5. So we can just do x times 5, which we already done over here. Right? So this is a form of drawing. You get what I'm trying to say? Instead of like working it out, instead of doing all this for loop again for the star operator of matrix times, for the star overload of matrix times RHS, we can just do like, we receive a scale object and a matrix. But here we receive a matrix object followed by a scale, by the scale factor. So instead of doing it the other way, the opposite way, why not we just call this function, do it for us. Then we don't have to repeat ourselves. And it's just one line. It could just be one line. Like this. Right. See, instead of doing another 5 more lines, we just make it a 2-liner. Or it could even be even simpler like this. But it's quite hard to read. So do it like that. Right. This one I will explain. Do I have to explain this? No. Actually, yes. Okay, this one we didn't use the bracket operator. Right. For this one. Oops. For this. For this we use the for range. Right. We know how, the range for loop. You know how the range for loop works is that it will assess every element inside and then just store it, print out as whatever. So for every element in data, we take out the row, the top row, and then from the top row, we get the value inside. Then whatever the value inside, we store into OS. Right. Then if the value is the last one, okay, if the value is not the last one, the dot vector back up, not the last one, then we put space so that we get, oops, so we get a space for all of everything. Then for every after every row, we will slash n, and get the next row. Right. So maybe you guys are like asking, why didn't we do it like that? Why must we do it this way? Let's say if you want to assess something specific, right? If you want a iterator, this one doesn't give you an iterator. It just loops through recklessly all the way to the end. It doesn't stop for anything. So how will you know what's going on, right? So some functions need the iterator. If I can find one of those. Yeah, like this. I think this no need iterator. I think some of them require iterator, some of them don't. Like this one requires the iterator. Because you need to know your R and your X, and your X and your C. Otherwise you just recklessly going through the data inside the matrix, it won't make sense. You can try by yourself. Maybe you can figure out a way to do it, but it's better to use brackets overload so that you have a solid iterator. You know what's going on. Okay, then now we are now since I already explained this part. This one, okay, I can show you another form of drawing, which is boolean. So we have our equal operator, which we know if we false it there's a mismatch, return true will be the same, right? And just compare all the values inside, right? So we need the iterators because we are assessing two different type of things, data and RHS. If you are only assessing one type of data, one type of matrix, then we are good to go. But since we are assessing two different matrices, we will need the iterator to go through it for us. Right? So equal, compare everything. If row is not the same, return false. Column is not the same, return false. If anything, any of the data inside is not equal, you return false. If all these check out, you return true. Right? So that's how we always implement our equal operator. So how do you implement our this for funcs? Right? You need to do funcs as well. So what if it's not? If you want to do the other opposite way, we just return the negation of our Boolean operator. Right? Makes sense, right? It's just the opposite, which is what this is doing for us. So this is another form of drawing. This one you can't do drawing because it's counts. Alright, and then maybe you can. No, you can't. That fonts two different type of thing. Okay. Then now since we have done those, what else have we done? This is done, this is done, this is done, done. We left this one. Okay, so I said today was fast, right? So for plus equals minus equals star, I guess I already found spot the answer to this over here, where this is the same as this. So if you really implement our plus operator, we want to do plus equals. Where is it? Yeah, over here. Now we just call the plus operator to do it for us. So this is our matrix object equals to our matrix object plus RHS, right? Which is the same as this plus equals RHS, right? Same as star this plus equals RHS, isn't it? Same thing for our minus equals. Same thing for our matrix scaling. Yeah. What's this? Multiply value with lambda. Okay, this is our matrix multiplication. This is our matrix scaling. Yeah, and then I think in the driver file, right? Okay, let's go. They can do let the star equal. Yeah, you can do star equals and don't test it. Okay, but they could have done matrix, or they can only do it like this. Yeah, so this is fine. Star this time RHS and just return. They can't do matrix. They can't do scalar times equals matrix. Doesn't make sense. But matrix times equals value, a scalar makes sense. Right. Then that's it. That is the end of this drive principle. Right, super fast, right?